Well, thanks again, Jimmy, and thanks for the introduction to speak here today. So my name is Heather Couture, and this talk is about foundation models for pathology. So we're switching domains here. The development of new computer vision solutions has often been long and iterative because each new solution starts from scratch, a new model for each new task. Each model is time-consuming to develop. But if we take a step back from computer vision, we've all seen how LLMs have simplified development for language models. There are now no-code solutions to fine-tune an LLM and create your own custom chatbot. This approach works because of pre-training on massive amounts of unlabeled data. And until recently, this would have been impossible for pathology. But large data sets, some public, some private, and foundation models trained on them have created a similar paradigm shift for computational pathology. We're getting closer and closer to interactive solutions that can assist pathologists. Foundation models bring many advantages that I'll talk about in a few minutes. They can be applied to applications in image analysis, diagnostics, drug discovery, clinical trial planning, and more. My goal for this presentation is to help you understand what is possible with foundation models for pathology. For those of you who are beginners, you'll get a general understanding of what a foundation model is and its benefits. And for more experienced practitioners, you'll learn about different ways you can use foundation models and also about when to be cautious. If something in this talk resonates with you and you'd like a deeper discussion, I'm also offering the opportunity for a free call, and I'll provide details about that at the end. But first, who am I? Well, most of you I haven't met, so I'm Heather Couture. I'm a computer vision consultant, and I've worked with a variety of startups, including those listed here. I've been a keynote speaker at the Mackay workshop on computational pathology, and I've contributed to a number of publications like Scientific American, The Pathologist, and the Digital Pathology blog, among others. I have a weekly newsletter called Computer Vision Insights and a podcast called Impact AI. Academic-wise, I have a PhD from the University of North Carolina. And my story in pathology really starts during my PhD. We were working with images of breast cancer and trying to predict molecular properties like receptor status and genomic subtype. When trying to predict biomarkers, you only have patient or slide level labels. Without detailed annotations, this is called weakly supervised learning. So labels are available for each patient or slide, but labels for tiles within them are unknown. It's up to the model to infer the latent tile labels or to naively assume that all the tiles in the slide fit the patient label. So a basic model for predicting biomarkers from whole slide images might go something like this. Divide your image into tiles, extract features from each of the tiles, aggregate the tile features, and then predict the class. When I was first working on this about 10 years ago, our initial way to extract features was simply to take a model that was pre-trained on ImageNet and use that to give a feature embedding for each tile. And this worked. But even a few years later, there were much better solutions. We've come a long way since I started working on this problem. This is by no means the only use case for a foundation model. I'll talk about the others in a few minutes. But it is the use case that motivated me in learning about foundation models. Self-supervised learning has been around at least since 2015, but not necessarily on the large and broad scale the past few years. The term foundation model was coined at Stanford in 2021. So just to be sure we're on the same page about what this is, a foundation model is any model that's trained on broad data, generally using self-supervision at scale, that can be adopted, e.g. fine-tuned, to a wide range of downstream tasks. Self-supervision means learning features without labels by solving a pretext task. The most common self-supervised framework used for pathology is Dino v2, a framework developed by Meta. It learns features from unlabeled images using a student-teacher framework combined with masked image modeling. The first publicly available model for histology appeared around 2022. But it wasn't even called a foundation model at the time. It was just still called self-supervised learning. Today, there are at least a few dozen foundation models for histology. The key is that they are adaptable and generalizable. Once trained, they can be fine-tuned for a variety of different tasks. They can also be kept frozen so that you simply use the embeddings for another task. Or you can even use continuous pre-training, which involves additional phases of pre-training on different data sets. So why use foundation models? I'm going to go through four different reasons here. There are probably others, but these are the main four that come to me in working with pathology. The first is if you're working with these gigapixel images and weak supervision, so the patient or tile level labels that I mentioned earlier. The typical solution here is to take your whole slide image, divide it into tiles, extract features from those tiles, and then aggregate them with some kind of multiple instance learning. And like I said, initially, we just use ImageNet to extract those features. But models that have been pre-trained on histology images give a much better representation. They give a tile embedding that's much more generalizable. So this solution is great when you're trying to predict slide or patient level characteristics. Things like mutations, genomic subtype, hormone receptor status, patient outcome, treatment response, things like that. But keep in mind with this approach that this information flows in one direction, from tiles to tile embeddings, then through the slide level model to make a prediction. There's no way to add contextual information to the tile embeddings. Such a model might miss out on the information that pathologists get from zooming in and out and panning around a slide. The second reason you might choose to use a foundation model is if you have a limited amount of labeled data. So this graph is just a toy example from the patch chameleon datasets, where I pre-train different self-supervised models on this dataset and then use the embeddings to train a supervised linear model to predict the class of these patches. And you can see with an ImageNet-based model with no fine-tuning, these features are not nearly as informative as the ones that were pre-trained on the patch chameleon dataset. And this is especially true at the left side of this graph, where you only have a few labeled training examples. On most benchmarks, pathology foundation models outperform training from scratch or using a foundation model from another imaging domain like ImageNet. But that's not always the case. In the plot on the left, with only 1% of a labeled training set, the foundation models are superior. But on the plot on the right, the task-specific models sometimes win. So that's the task-specific one is the blue one compared to Uni and Virchow. So it depends on your task and how much training data you have. For segmentation in particular, I often see the task-specific models beating the foundation models if you have enough labeled data. The third reason you might choose to use a foundation model is to assist with robustness to distribution shifts, batch effects, and bias. So distribution shift occurs when the statistical distribution of data changes between the training and inference stages of your machine learning model. This phenomenon violates a fundamental assumption in machine learning that the training and test data are drawn from the same distribution. And then we also have batch effects, which are a systematic difference in data caused by technical variations between groups of samples processed at different times or in different places, rather than the true biological differences. And both distribution shifts and batch effects can lead to biased models. These are some of the most common challenges that I run into on projects. Sometimes the challenge is obvious and known at the start of a project. Other times it's more subtle. But identifying and addressing it is important because it can decrease the accuracy of your model when deployed. It creates the potential for biased or unfair outcomes. It can cause unexpected behavior in real-world scenarios and can cause safety concerns, especially when we're talking about medical applications. The most widely known and frequently addressed cause of distribution shift is scanner variability. Each scanner produces a different color profile for the hematoxin and eosin stains, but that's not the only source of variation. Pathology labs independently determine tissue section thickness standards for their workflows, ranging from 2 to 5 microns. But additional variability in section thickness arises from factors like equipment maintenance and calibration, as well as technician skill. As section thickness increases, the tissue gets darker, and there's more blurring. Thicker sections also have less defined nuclear and structure boundaries. Plus, there are also artifacts caused by the slide preparation and image acquisition process. Some examples are out of focus regions, fading, tissue folds, foreign objects, and bubbles. The prevalence of these artifacts varies with the data set. So we've looked at scanner, tissue thickness, and artifacts. These are some of the tissue preparation factors that can lead to slide images being from different labs having a different appearance. Next, let's look at how foundation models handle these batch effects. The authors of this paper experimented with 9 different foundation models on 2 different data sets with and without stain normalization. They used the tile embeddings to try to predict the site a sample came from. All models achieved 75 to 97% accuracy, with more recent models performing higher. Stain normalization lowered the accuracy, but only slightly. This means that all foundation models tested encode site-specific features that a model could use for shortcut learning instead of focusing on the biological features for solving a task. And stain normalization alone does not resolve this problem. This study proposed a medical center robustness index to evaluate to what degree biological features dominate compounding features. They used 10 different pathology foundation models to extract image features and formulated the robustness index as the ratio of how many of the k-nearest neighbors represent the same biological class versus the same medical center. So values greater than 1 are more focused on biology, and those less than 1 are more focused on the medical center. Only one model, Virchow 2, achieved a score greater than 1. This raises concerns about whether apparent diagnostic accuracy is actually based on site-specific confounders rather than true biological differences, potentially limiting generalization to new medical centers. Those building and using foundation models need to be aware of this potential bias. So we have concerns about foundation models because they encode site-specific features. But how do they actually impact bias and generalizability? This first study I have here calculated demographic stratified metrics in predicting IDH1 mutation, lung cancer subtype, and breast cancer subtype. They found that using self-supervised learning models trained on histology tended to reduce the performance difference between groups compared to models pre-trained on other types of imagery, like ImageNet. While self-supervised learning reduced the discrepancy, it did not eliminate it, making it clear that this is an important challenge still to be tackled. Of the more than 24 techniques to tackle distribution shift, self-supervised learning is still the top contender. So foundation models don't solve the generalizability challenge, but they do provide a significant improvement. The fourth reason you might choose to use a foundation model is for rapid prototyping. So if you already have this foundation model trained and it knows how to represent the type of data you're working with, you could fine tune it, or you could just keep it frozen and use the embeddings to train a simple linear model for classification or regression or whatever task you're working on. That enables you to get up and running and get your model going much quicker than if you're training something from scratch. But there's still a couple things to keep in mind here. And that is, whatever model you select for production use will be involved in processing every whole slide image that you'll need to do inference on. And that processing uses electricity and produces emissions. This example is for Germany, but every region has a different mix of fossil fuels and renewable energy, so these percentages may change. Larger models use more electricity, which produces more emissions, assuming the energy source stays the same. This plot doesn't include many of the recent models, but they are getting larger and larger, although they're not yet as large as most LLMs like PaLM in the upper right corner. With increased model size comes increased emissions. Sometimes smaller models or task-specific models perform almost as well as gigantic foundation models. So there's a trade-off here. Perhaps foundation models are best for initial prototyping with limited labeled data, or when you're using the same frozen embedding for multiple prediction tasks. So we've looked at 4 different reasons you might choose to use a foundation model. The first is with gigapixel images and weak supervision. This is one of the primary motivations for the initial development of foundation models for pathology, and is very much a great use for them. But keep in mind, this type of model doesn't carry information up and down across the scale, so it can't replicate the way a pathologist might analyze whole slides. The second reason was if you have a limited amount of labeled data, and also a great reason for using a foundation model. But keep in mind, when you have sufficient training data, full supervision sometimes is the top performer, and I've seen this more for segmentation than for other tasks. We've also seen that foundation models tend to improve the robustness to distribution shifts, batch effects, and bias, but site information is still encoded by all of these models. Some foundation models are more robust to medical center differences than others. And the fourth reason was if you want to rapidly prototype a model, you want to get up and running without all the work it takes to train a model to learn a representation for your data. And this, again, a great reason for using a foundation model, but keep in mind the training and inference time and the energy use, especially if you've chosen the larger model. So these are all great reasons for using foundation models, and I'm not at all trying to discourage you from using them. They bring a lot of benefits. I just want you to be aware that they are not a panacea, and to think carefully about your use case. My main focus today has been on tile-based foundation models, and that's very much where we started in the pathology domain. But before wrapping up, I want to give you a brief hint at some other cases for foundation models that go beyond tiles. The first one is in the multimodal domain, combining H&E histology with language. This is one of the first vision language models for pathology, called CLIP. And if you're familiar with CLIP, it's just a fine-tuned version of that using 200,000 pathology images and natural language description pairs. So that's one of the first multimodal models in this area. The second is that we don't need to stay at the tile level. There are now foundation models for whole slide images. One of the first ones published is called Prov-GigaPath. It uses a slide encoder trained with Dino v2 for tiles. And at the slide level, it learns the embeddings by using a masked autoencoder. Because whole slides have thousands of tiles, they need to do some modifications, and they used a long net to handle the number of tiles per slide. And they were able to train this using 171,000 whole slide images from 30,000 patients. There are other more recent variations of this, but this is the first one that was published. And then going back to the multimodal domain, we can combine slide level models with other types of data. So in this case, instead of using the masked autoencoder to learn a slide level model, Tangle was trained by combining the slide representation with gene expression for the slide. So they used a contrastive model in order to learn that representation. And then once trained, the slide model can be used as a representation for some other downstream task. And finally, we have CPATH Omni, a vision language model for whole slides. It was built using the Dino v2 base Virchow 2 model for image tiles and CLIP for vision language alignment. And it was trained in 4 different stages. First, the vision language alignment, followed by learning tasks like visual question answering, classification, and captioning on patches. This third stage moves up to the whole slide and focuses on generating pathology reports. And the last slide combines slide and patch level tasks. This model works for captioning, subtyping, and visual question answering. There are many more recent publications that you can dig into if this is of interest. Each brings us closer to a system that may one day interact with pathologists. So to summarize, we've looked at 4 different reasons why you might choose to use a foundation model in modeling pathology images. So I don't think I need to repeat those because I went through them a couple times. But the second section on where things are heading, we looked at a couple multimodal examples and especially vision language. But there's also opportunities for incorporating genomics, radiology, clinical data, and other types of data that might be related to patients. There are now slide level foundation models, and some of these have shown great results. But I'm even more concerned about the potential for bias due to distribution shift and batch effects at this level. And so far, there's no research that really investigates this challenge at the slide level. There are also now models that generate pathology reports and chat bots that you can use to interact with your slides and pose questions and get answers. And we're heading more and more in the direction of agents that clinicians will be able to interact with. This technology is evolving rapidly. In the startup world, there have been many new advancements. Modella AI received FDA breakthrough device designation for their chatbot earlier this year. Many companies are using foundation models for predicting biomarkers, companies like Paige, Owkin, and Imogen, among many others. There are startups like Bioptimus and Noetic. They're integrating different types of biological data, including histology. And there are startups dedicated to building foundation models like HistAI. For most situations, you don't need to build your own foundation model now. Somebody else is already doing it for you. And there's also Proscia's platform that is used to easily use the embeddings from slides. Foundation models are getting larger. This worries me for a few reasons. This research can become inaccessible to academic groups and the increased electricity usage and emissions I mentioned. And just going bigger in terms of data and models can stunt our creativity and an initiative in better understanding the data. So for anyone training foundation models, I urge you to try something different. And for everyone to think about new use cases. Use them as a tool to enable your own impactful applications. It's an exciting time for pathology. If you'd like to stay up to date on computer vision, especially for applications in people and planetary health, you can sign up for my newsletter, Computer Vision Insights. The QR code is at the top right. And if something in this talk resonated with you and you'd like a deeper discussion, I'm offering a free Pixel Clarity call in which we'll dive into your unique challenges and goals. I can help you connect data, modeling, and domain expertise to build more trustworthy computer vision. You can book this call through the Calendly link shown here and the QR code on the left. You can also reach me directly by email. And other than that, be happy to answer any questions.
Thank you. So I've also gone ahead and included a few additional links on how to get in touch with Heather, but also to check out the Impact AI podcast. The links are there in the chat. Let's take two quick questions. I'll try to kind of summarize one of them. The question revolved around foundation models in regards to licensing, meaning that in your estimation, how many of these models are going to be open source? How many of them are going to have kind of commercial restrictions, and how many are going to be proprietary? So I guess the question revolves around how accessible are these models to researchers where licensing may play an issue.
So you're very right to be concerned about that, but the good news is the majority of them are available, open weights. You would have to check the exact license as to whether you can use them for commercial use or research only. And yeah, this is just one example, and this chart is outdated. I put this together, I think, in January. So there are definitely more foundation models since then, and these are only tile level ones. The ones with the asterisks have open weights. So that's the place to start, and you can see the significant number of them are available for at least research use.
And then the next question is a more generalized question, which you probably have a good answer to, is for someone who wants to start applying foundation models to pathology. I think in that last slide that you showed, just the sheer abundance of foundation models, where is the best starting point for understanding foundation models and which ones may be most applicable to the sort of research that you want to conduct?
So there's a few things to keep in mind. You want to you want to think about your use case. Is a foundation model the right thing to start with there? And for a lot of cases, it is. You also want to do a bit of research on what each foundation model was pre-trained on. If you're working with breast cancer, for example, H&E breast cancer, you want to be sure that model included some of that data in its pre-training. If instead you're working on immunohistochemistry, some of these foundation models included IHC in addition to H&E, others did not. So it would take a bit of research looking into the papers to see what they were pre-trained on, but that is definitely worth doing if you're going to select one. The other piece of advice is just experiment. Pick three, maybe the three smallest so that they're faster to run. If you're just getting started, pick three and try them. See how they compare. Each will perform differently, and you'll be able to see from that if that's a good enough start or if you need to investigate further.